A variable is an event or observation that varies over time or by person to person. When we are dealing with the relationship between two variables, we are concerned with correlation, and our measure of the degree or strength of this relationship is represented by a correlation coefficient. This is usually the Pearson product moment correlation coefficient, represented by the symbol R. Consider research questions that we might ask that involve a correlation. Does the incidence of breast cancer vary with the amount of sunlight in a particular location? Does the accuracy of performance decrease as speed of response increases? Let's think about how do we know if the correlation matters? Well, it must be significant in that the relationship is strong enough to be unlikely due to chance. It must also be meaningful. It does not imply causation. We cannot make that conclusion, that one variable causes another. However, once we have found a significant correlation, we can investigate further and perhaps do an experiment based on the theoretical foundation that one might cause the other. Next, we will discuss correlation coefficients in scatterplots. Remember that most correlations represented by the Pearson product moment correlation coefficient, which ranges from -1 to 1, where 1 is the highest strength of relationship. The independent variable or the predictor variable is usually represented on the x or horizontal axis. The criterion variable or dependent variable is shown on the y or vertical axis. As we look at the scatter plot, we've drawn a regression line or a line of best fit, which represents our prediction of the dependent variable for a given value of x. The closer the points are to the regression line, the stronger the correlation. Notice in our example on the slide that all the data points are clustering together somewhat in scores on the x as scores on the x-axis increase. So do scores on the y-axis generally. Therefore, we can draw a somewhat straight line through the data that represents the general relationship of the data. In this case, since the slope is positive or increasing, we know that it is a positive relationship. In other words, as one variable increases, so does the other. In a negative relationship, we would see that one variable increases while the other variable decreases. Other variables can influence our results. Just because two things are related does not mean that there isn't a third or fourth variable that is truly responsible for the relationship. For instance, grass growth may be positively correlated with vitamin D increases in the body. Theoretically, this does not make sense. Instead, we logically know that sunlight increases both variables. Perhaps we need to look at the correlation of sunlight frequency with each of these variables rather than the relationship of one variable to the other. In this case, sunlight would be considered as a mediator or in-between variable that is the true reason for the relationship. A moderator is something that affects the relationship that already exists. For instance, a study might find that students do well with one-on-one tutoring, but that relationship is even stronger if the tutoring is done by someone with higher education. In this case, the relationship already exists between one-on-one tutoring and student success. However, their relationship can be increased or decreased based on the skill of the tutor. As we look at the scatter plots, we will find that they do not always follow a linear relationship, wherein we can draw a regression line that is straight through the middle of the data. Think about cognitive skills and age. As we age from birth, our cognitive skills increase, but as we start to advance in years, cognitive skills often start to decrease again. Therefore, the relationship between age and cognitive skills is not linear. Rather, it goes up and then back down. This example is a curvilinear relationship. The correlation coefficient that we want to compute is based on a statistic called covariance. Covariance is basically a number that reflects the degree to which two variables vary together. Generally speaking, we might say that high scores on one variable tend to be paired with high scores on another variable, resulting in the covariance that is large and positive. However, if scores on one variable are paired about equally often with both high and low scores on the other variable, our covariance will be near zero. If scores on one variable are associated with low scores on another variable, the covariance is negative. For example, we might think about how our weight varies as our level of exercise varies. We might also consider how weight varies as our food intake varies. In so doing, we might establish general trends that shed light on the relationship. Covariance is a key component in the formula to calculate the correlation coefficient. The correlation coefficient formula is the covariance divided by the standard deviations. In this light, we see the formula drawn in two different forms that are equivalent. We start to understand that R can be viewed as a measure of the degree to which the covariance approaches its maximum. Take a look at the book. See Table 9.2. As we look at the data, we compute each of the components that we will need for our formula to calculate the Pearson product moment correlational coefficient. The covariance between two variables can be calculated as in n times the summation of all products between x and y values minus the summation of all x multiplied by the summation of all y's. In this case, that equals 5.74. After calculating our standard deviations for both variables, we multiply them together as the dividend in the equation. Then we divide the covariance by the product of the standard deviations. The result is 0.365. Is this a strong correlation? Positive or negative? Remember that strength of the relationship has nothing to do with whether the relationship is positive or negative. Rather, a relationship is stronger as it approaches 1 or negative 1. As the book points out, a correlation of 0.365 does not mean that there is a 36.5% relationship. Instead, it is a number on the scale that does not represent a percentage. As a general rule, I consider values below absolute value of 0.4 to be weak relationships, values between 0.4 and 0.6 to be moderate relationships, and values above 0.6 to be strong relationships. This guideline may differ from textbook to textbook and by researcher. Then we take a look at Spearman's correlational coefficient for ranked data. Obviously, it is used with ranked data such as first place, second place, third place. It measures the linearity of the relationships between the ranks. The main difference is that the data are not measured, they are ranked. Spearman's correlation coefficients can be used to measure only monotonic relationships. The relationship does not have to be linear. Although the line does not have to be straight, it should be continually rising or falling. The correlation coefficient can be affected by characteristics of the sample. If, in our example of age and cognitive skill, we'd only used individuals aged 0 to 18, that would be an example of a range restriction. Range restrictions alter the correlation between x and y from what it would have been if the range had not been so restricted. If a relationship is not linear, we cannot logically compute correlation at all. Also, when we calculate a correlation, we must have homogeneous subsamples. In the example from the book, interpretation of certain research questions, in the example from the book, sample contains both males and females, which is normally good. However, it may confound a clear interpretation of certain research questions and findings because males and females are physiologically and anatomically different. They would independently produce different correlations between height and weight. However, by including both heterogeneous subsamples, neither group nor the intended group is properly understood. Next, we'll talk about outliers.